Hello and welcome to my ideal gas equations presentation. Today I'll be going over ideal gas law, partial pressures, and particle speeds. Here we have the question I'll be going over today, question 4, part 1, 2, and 3. I'll be starting with part 1. I will in fact be splitting question 4 part 1 up into two sections to save on difficulties. Question 4, Part 1. A sample of 255 grams of neon gas occupies 3 decimeters cubed at 122 Kelvin. Using the ideal gas law, calculate the pressure of the gas. Well, what do we know? We know the ideal gas law, and we know everything except the pressure. We know the volume is 3 decimeters cubed, the temperature is 122 Kelvin, and we can work out the number of moles by using the mass of neon gas given divided by the molar mass of neon to give us 12.64 moles of neon gas. And I have elected to use the R value of 0.08206 litre atmospheres per mole Kelvin, purely because it makes things simpler, because I can just transfer the decimeters cubed straight into litres, because it is a one-for-one relation. Now, we can first of all stick our units into this rearranged equation to check to make sure we do receive atmospheres as our final unit. And as you can see, the moles cancel out, the kelvins cancel out, the litres cancel out, leaving us with just atmospheres, which is ideal for pressure. Now we can substitute in our actual numerical values to give us an atmosphere value of 42.2 atmospheres. A pressure value of 42.2 atmospheres. Now the problem with this is that the gas, in reality, is not ideal. If you imagine this screen is a container, then these gas particles, in fact, take up room on the screen. They are not massless. And another problem is the interactions between them. In both the pressure and the volume sections of the ideal gas law, we do not account for the volume and the pressure of the gas. We need to, because when particles pass by each other, they do in fact interact and curve their trajectories, resulting in a change in pressure. So we need to have a version of the ideal gas law where both the volume and the pressure account for the volume and the interactions between the molecules in the gas. And here we have said equation. We have the pressure, which is adjusted to account for the interactions of particles in the volume given, and we have the volume, which is accounted for the number of moles of gas. It is effectively the volume minus the volume of the gas, and the nRT stays the same. So using this, and using what we know, we've been given A and B in the question, so what we need to do is rearrange for P again, which we can do in the second line down, but also we can substitute in our units again to ensure that we do in fact end up with atmospheres. Now what I've done here is I've taken the A and V section and just shown that there are in fact no units there, because decimeters to the 6, decimeters minus 3 squared just goes to decimeters minus 6, which cancels out. Moles to minus 2, moles to the 2 cancels out. And on top we have moles to minus 1, Kelvin, Kelvin minus 1, atmospheres, which is on its lonesome, decimeters cubed, and then decimeters cubed minus decimeters cubed, moles to minus 1, moles, so the moles cancel out, decimeters cubed minus decimeters cubed, the units still remain, but you can divide decimeters cubed by decimeters cubed to get no units, so we are left with just atmospheres. Now we can substitute in our values, our numerical values, to give us a pressure of 41.7 atmospheres. Comparing this to our previous value of 42.2, we have a change in 0.5 atmospheres, which is pretty significant. Now, 40 grams of helium gas is then added to the neon gas in the container without changing the temperature or the pressure. Assuming ideal gas behavior for both gases, calculate the vapor pressure of the helium in the system. Well, the first thing to work out is how many moles of helium were added. Now we know that mass of helium, and we know the molar mass of helium, so we can work out the number of moles of helium, and we had the number of moles of neon, so we now know there are 22.63 moles in total. Now the pressure was exactly the same, but the mole fraction we can work out by doing the moles of the substance, in this case moles of helium, divided by the total number of moles, which we just worked out, both of those, to give us a molar fraction of 0.4414. The pressure, as mentioned in the question, is unchanged, so we just take the previously calculated pressure, times it by the molar fraction, to give us pressure on the helium of 18.4 atmospheres. Finally, for this system, sketch the Maxwell Boltzmann distribution for each of the helium and the neon, and determine the root mean squared speed for each. Well, here is my sketched graph of Maxwell Boltzmann distribution, and as you can see, the neon is slower in terms of speed, meters per second, than the helium is on average. The areas under the graph are supposed to be roughly equal because the number of moles of neon is 12.63 and the number of moles of helium is 9.99, but I didn't feel the graph accurately represented that, so I figured I would say it out loud. One thing to take into account is that the speed is effectively reliant on the temperature divided by the mass, but because the temperature for both of these gases is 122 Kelvin, we know that the speed will be dependent on the mass of the particle. So the smaller the mass, the faster it will go. So He, as we said before, as we showed in the graph, He will be faster. Now the root mean squared can be calculated by using this equation. 3RT divided by MR is equal to U RMS, where U is the speed. Now we have temperature, 122 Kelvin, we have the MR, and we have our value of R. So why don't we just sub everything in, units first, to make sure everything works out, and it doesn't. It doesn't work out. So what can we do but try again? We can, first of all, keep using the same value for temperature because Kelvin is pretty consistent, but instead try a different value of R. Joules per Kelvin per mole. Now what are joules? Joules are in fact kilogram meters squared per second squared, giving us the units of R to be kilogram meters squared per second squared per mole per Kelvin. Now we have R in kilograms, so it makes sense to have our MR in kilograms per mole. This gives us, when working through our units, meters per second, which is what you would expect for a value of speed. Works like a charm. And here we have substituting in our values on the left into the equation, gives us a root mean squared speed of 872 meters per second for helium. And then substituting in our root numbers to give us a root mean squared of 388 meters per second for neon. Now remember, these are gases at 122 Kelvin, so they should normally be in the thousands, but because we are at maybe roughly half room temperature, no, 1/3 of room temperature, we are a lot lower than room temperature, so these will not be going at thousands of meters per second. We can compare these to my graph that I drew earlier, and we can see that helium is indeed faster on average than neon, which is what we would expect from results like this. So, anyways, references, and yeah, thank you very much for sitting through my presentation, and